We have a great team of software developers, both PhDs in physics, of all matters. Bruce Klapoff, PhD from here, University of Texas, and Joaquin Ambia Garrido, PhD from University of Houston in physics. And they are the heads of the UTAPWeLS development. As you know, many of you talk to them, send emails, and they're very happy and very expedient to make all these changes. So today they are going to talk about they highlight the developments that we think are interesting, and then there's a demo place also as part of the presentation. So my task is, after introducing you, is to bring everybody back here, okay? And here is your...
Thank you, Carlos. Thank you for the introduction. Okay, so as we do every year, we're gonna start by having a talk about what's been happening in the software front. We're going to start talking about how the software has been changing regarding standards and user friendliness, things that are very important. As much as they might seem very simple and sometimes silly, they have an impact. Then we're going to be talking about the things that everybody agrees have high impact, the new methods and the new modules that we have, or the ones that have been updated. Then we're going to talk about the user feedback, all the comments that you guys have given us and how we've done some developments. And I wanted to say that this year we had more people making comments and getting feedback and developments faster than otherwise. And so it's great to have more people making comments and more people getting updates the way they want them. And then lastly, we're going to talk about what we want to do with UTAPWeLS in the future. What are the developments that we're expecting to have in the next few years? And again, to reiterate that, we want your feedback. That's what makes the software relevant. That's why an academic software can stay relevant. And lastly, we're going to talk a little bit about support and outreach. Things have changed in that front, I think, for the better. And let me know if you agree. So one of the things that you may not see right away, but you would notice if you pay attention, is we've been changing the standard for the plots that we use. MATLAB made a change about 8 years ago, but that change, they did it about 8 years ago, but really getting it to work properly has been the past 2 or 3 years. So in the past 2 years or so, we've been making the update, everything to this new standard they call it the UI figure, user interface figure, and there's a lot of things that come with it. A lot of it happens in the back end and you will not see it, but a lot of things actually you will end up seeing. You might notice that the interactions get a little smoother, that's the whole point, and the render is faster, so the plots should be easier to interact with. And they do have a cleaner and newer look. Again, things that you may think that they don't matter, but they actually do when you spend actually quite some time with the software. And they've updated some graphical components. This actually is where you start seeing some of the things that do have a significant impact. There's new buttons, new labels, new panels, new tables. For example, the tables before, whenever you modified something, they would go back to the first cell. Now that doesn't happen anymore. That's not anything, well, we didn't do that. That was MATLAB finally fixing that bug, but they never fixed it in the previous one. They fixed it in this one. And when you have a big plot, it made a difference. Or a big table, it would make a difference. More operations are allowed. For example, now you can drag and drop. That's something that Carlos had been asking for many years, and it was not so easy. It's not so straightforward, but now it's possible. So these are all the simple things that you get just because we moved to the new standard. Also, another little thing that you will notice is there's this label. This looks like something that's been modeled, and also a little bit like a longhorn. So that's an icon that you can see, and that's when you see something like that in a figure, you will know that that's using the new standard. All right. That also allowed us to have better interactions with the graphics that we have for the crossplots. We've had the crossplots for a while, but we did an overhaul on them. Now we have the overlays a little more straightforward, so and it's easy to change. I'm going to have a quick demo just to show you how easy it is to go back and forth. We've had this module for a while, but it was very slow. Now it should interact. It should be very easy to interact. We have the sources here that they have been cleaned up. They follow the same path, the same pattern that we use for the track display. You have the source with the type, and then the curves and so on. Vertically, you have the X, the Y axis, and so on. You can show multiple wells. You have the units. You can change the units here. You can change the limits. It's a little easier to change the limits. We have some default limits that make things easier too. And hopefully you get to use it a little more. You can show multiple wells. I'm going to have a quick demo on all the little things that we've modified, and hopefully you see the value on that. Another thing that's possible now with the new standard is now we can use the native zoom, pan, and save. This is good because it saves us time programming. We don't have to make a function for doing all those things. It was not possible, not because they didn't have it, but because it was not going to interact with the rest of the graphics. Now they play nice, so we can have those things. And there are some things, for example, you can save this image directly to a file. That's something that they included into that, and I think it's a nice benefit. So we have all those things going on there. Now, some of the things that are more attributable to us, we have the horizontal track display. We are reintroducing this track. It's exactly what it sounds like. You can have either measured depth or the true horizontal length as your independent variable. And along with that, we included a curtain plot where you can follow the trajectory in a vertical projection. It's mostly used for UDAR, but you can use it for other things, and you can use it as a. We don't want the UDAR developments to stay completely independent. We want to get this feedback and go back from UDAR and integrate it into the rest of the well logs that we have. We also have reintroduced the depth, shift, stretch, and squeeze. We not only reintroduced it, but we expanded it. We have an algorithm that works with it. We have a quick demo on this. Hopefully, it makes it clear why we did it. You can also do manual adjustments. This algorithm it will automatically identify the locations that need to be shifted, and that's great. But we know that sometimes you need a little refinement. You can also do that manually. You can have as many logs as intended. So one of the biggest developments for this year was the joint interpretation, the compositional joint interpretation. That's the name we're giving it. And it's a module that is used for interpretation. We did go through a complete overhaul. We have had something similar to this module for a few years, 3 years, something like that, maybe 2, maybe 3. And it was working, but it was asking for too much from the user. That's the bottom line. It was asking the user to provide some prior probabilities, so a good guess of where the final results were going to be. That was not always the case. And what would happen is that the user, when we were working with sponsors, the user would have to start with a not very good guess, and then given the results, would have to refine those guesses, and those guesses were not always easy to refine. In principle, you could get, once you did it for one well, you could do it for as many wells as you wanted, but it ended up being a little too complicated. So we modified it, and the biggest change was that instead of just assuming that you're going to provide those guesses, now we're going to try to find the absolute minimum, so the place where the outputs are matching the inputs as close as possible. This was in part developed by Ali Ekbali. And then from there, we can estimate uncertainties using the previous algorithm that we had, but once we know where the solution really should be. Besides the complete overhaul in the back end, we've done some design changes. If you remember, this used to look very different. It was even more wordy, and it had less information. So something we try to do in UTAPWeLS in general is we try to keep a modular design. So we have panels, and in every panel you have things that are just related to that one thing. In this case, for example, we have the inputs, which are the properties you're going to match, density and so on. So it's very clear that these are going to be the inputs. You can add them, remove them, you have the weights. There should be no, or we believe there should be no questions about what's going on there. Then you have the outputs, what are you expecting to get? You have the shale structure and so on. And similarly, you have formation conditions and these other options that we're going to go into them a little more. And something that's different here is that, and this goes very much in line with what we think UTAPWeLS should be, everything that is going to affect the result, everything that is going to affect the functionality of this module, you're going to see here. That was not always clear, and it's not always clear in many places. For example, the temperature. It was not there, it was implicit. We want to make sure, here is the temperature. You know what that is. So for example, in that line, the formation conditions are something that was assumed to be there, and there was always a default value that was probably a good guess, but now it's in the same window. So you know exactly what's going in there, and you can modify that. And we've seen a lot of people that saying, oh, well, actually the temperature might be different. So instead of having to go to another module where you would change the temperature, which was always valid, a valid option, a valid alternative, now it's a lot easier to just type it here. And if you already made the calculations and you want something more interesting than just a constant, which is something you can do with other modules, then you go to those other modules. But if you want to modify something, you have it here, and at least you are aware of all the things that are going to affect the results of your inversion. Also, another, probably the biggest change that we had, besides the algorithm, from the algorithm point of view, I already discussed it, but also from the petrophysics point of view, the biggest change we had is that now you can consider invasion. We're going to have a little demo, and not only that, we're going to have a talk. Tomorrow I'm going to give a talk on what that really is in the back end. But all you need to know is that instead of inverting separately or just inverting for the formation zone for the non-invaded zone, you will consider a zone that is invaded and the measurements being different because they are in the invaded zone. And you can also estimate uncertainty, which is using the same algorithm we had in the past. Makes it simple, and it's clear, again, modular, a different panel saying what are the inputs that are going to affect that. You can also calculate some physical properties that are a consequence of the results that you would get here. This, you can calculate permeability, you can calculate hydrocarbon pore thickness, and well, the outputs are different, of course. Before we used to ask the user to provide a guess of the distribution, like I said, and it was a Gaussian mix, and you could do that. Now we only ask for a minimum and maximum value and an initial guess. And in most cases, the initial guess, it's only relevant for speed, but it's not going to be relevant for the final answer. And that's what we want to see. And then instead of showing each of these components in one big table like we used to do, we just have we have three buttons: one for the matrix, one for the shell, one for the fluid, which are the way we divide the composition of any rock in UTAPWeLS. Something else is that because we realized that in many cases the shale that you have is unstructured, we added that option here. Before we had only Thomas Tiver style options. We had laminar or dispersed or something, those type of things. But in many cases, we don't know what's the structure. And we used to have an option for that, but it was convoluted. It was something like only restrict porosity by non-shell porosity. And it's, of course, to me it was clear, but to the user, it was not always clear. And we didn't want to do that. When you say, well, it's just unstructured shale, it's very clear. And users, something that makes it easier for everybody to work. And it started here, but it's also now part of the palette and part of anywhere where we were considering shale structure, we can now have the unstructured shale. And then, like I said, in each one of these, you can modify the composition with this module that we've had for a little over a year. We showed an initial version last year. It's been streamlined and improved in the past year. And what you do in this module is, and I'm showing you the shale as an example because it's the most complicated, and basically the other two are a subset of this anyway. So you have the solids, you have the fraction for each of the components. For example, you could have elite muscovite quartz, and you could say what is the fraction of each of those. You have the formula for each of those two, which you can modify here. You can change the component, you can change the fraction. You can decide whether you want to fix it or not. By default, all of them are fixed. Basically, if you have a shale that you have designed, you believe you know the fraction of each of those minerals, you just fix them here. And when you do the inversion, they're not going to be changing. You can also allow them to change, but by default, they're not changing. And then you see the density. You can modify the density here. You can modify the slowness. And the neutron porosity, the photoelectric, you can also see it as inverse of migration length or migration length. You can see gamma ray. You can see all these properties are going to be calculated from the formula directly. using UTNU Pro. And so you will see those things here. You will see similarly the same things for the fluids. You can include the porosity or not. If you want to, you can fix the porosity in this case. For matrix, you can include porosity or not, depending on how the properties are going to look like. And then in the bottom, you have the total property. So in a way, this is like a petrophysical calculator for the component. So you would see for density, it's very straightforward. It's just a linear mix, so it's very easy to calculate this. But for photoelectric, for neutron porosity, for other properties, it's not so straightforward. So we've seen a lot of people using it not just for the inversion, but also just to see if the fractions that I'm using are actually going to make sense with what I expect to see in the field. You can, like I said, you can modify the formula, and the properties that are directly calculated using UTNU Pro are going to be modified just by modifying that formula, which makes it really quick. But that was one of the developments that you don't see, but we had to do so that this would work fast, is we made UTNU Pro a lot faster and more easily callable by MATLAB. So when you click here, immediately you see the results. Like I said, the porosity, you can modify the porosity. And right now we're using it as part of the compositional joint inversion. But there's other modes that you can use it for example, database, which would allow you to just design any shale or any matrix, and you can say, well, this is the shale that I want in all these formation zone or in these layers. It can be used for other things. We don't have it right now, but in the future we want to allow to have these for specific layers too. So and it's like an extension of the palette. Something else that we did, and this is small, but it's very useful, is now we have a new plot, very much related to the compositional joint inversion. It's just a cumulative plot for curves, easy, straightforward. You just select the curves, and they'll show there. We've been using it a lot for comparing it with results that you would get just using logs as input instead of doing the full modeling, which is what UTAPWeLS is providing. Something else that we've been doing is we've been slowly but surely doing some interaction, some developments that allow UTAPWeLS to interact with Python. The reason, first I want to tell you why. The main reason is because whether we like it or not, Python has been established as the common scientific programming language. It is the language that most softwares can interact with. MATLAB is great, but it's not free, and that's one of the reasons that it's not as easy to interact with, or it's not it's very easy to interact with it, but it's not as commonly linked to other softwares, just because you're asking someone to pay extra money for the same thing. Another reason why we want to do this is in Python, just because it's, again, the most common scientific programming language. You have all these libraries that have already been developed. You have PyTorch, Scikit, TensorFlow. All these are artificial intelligence libraries developed by Meta, developed by Alphabet, developed by all these top-notch companies. They decided that they wanted to make it open because that's how they would get more feedback, and they get the benefit on that. And you can use them if you move to Python, or if you interact with UTAPWeLS through Python. You can access all those libraries without any problems. We also have Rock5Py, which is a new library. It came out a couple of years ago, and it's everything in Python, all petrophysical calculations there. We have a lot of them already in MATLAB, but there's more. And if it's already available, why reinvent the wheel? That's kind of the reason why it's good to have that. And another big reason is that you can integrate UTAPWeLS workflows with commercial software. You could have something in UTAPWeLS talking to Python, talking to IP, Teglog, and Geolog. We've had small projects doing this, but I think this is one of the bigger benefits. You can integrate it. All these softwares have a Python window that you can just say, well, from IP, instead of saying, okay, I want to open UTAPWeLS and do this and do that, you could just say, okay, I have the script, I have the workflow that I want to do from UTAPWeLS. I'm just going to run it, and I can run it without even, I mean, you will need to use UTAPWeLS to design it, but once you have designed it, for some of the cases, we've had projects like that, that you don't want to do it in just one well, to really do it multi-well. You don't want to save it and go into UTAPWeLS, and you just want to, once you've established your workflow, you just want to run with that workflow. This is what is going to allow you to do that. Also, in the political point, we're not giving any priority to any specific software. That was always a problem whenever we started doing a connection with one software but not the other. It's not political, but it makes sense that everybody wanted to have the same development for everyone. So that we take a step back. Nobody has any complaints about that because everybody can just interact with what we do. In that line, something we've done is you can save UTAPWeLS projects as JSON files, which is not just accessible by Python, but anybody. JSON files, for those people that are not familiar with them, are just text file. They're human readable, which is great. And if you open it, you can see what's in there. But also the machine, it's organized in such a way that the computer is going to know this is a structure, this is a dictionary, this is all these different computer objects, and you can turn that into a project. And that project, even though it was saved in MATLAB, in UTAPWeLS, it can be opened in Python, and it can be opened just in Python by yourself and see anything. But the idea is that you can open it and turn it into a UTAPWeLS project in Python. These are just a couple of examples that we have. And if things go fine, we could go beyond the backend, beyond the scripting. We could have a user interface from the Python point of view, but that's to be determined, and that would be years from now. Something else, well, this slide, this is the beginning of this slide. I have different versions of this slide every year. Like I've said before, we love getting your feedback, so I'm going to show you some of the things that we've done very much because of the feedback that we've had. Most of them are small. Not that some of the big things that I've shown you are not because of the feedback that we got from you, but these are some kind of quicker turnaround. For example, we have now a new resistivity tool. And for this, I want to thank Lucas Blanes de Oliveira of Petrobras, because he wanted to have this tool, and he insisted we should have it. And he got in contact with Hal Burton, and I have to thank Jungsheng Hao and Tim Parker. They were very nice with us, and they told us, okay, these are the parameters you need to have. No, it's the variant that we're using is a UT variant, meaning that the software behind the scenes is a UT software. But we still needed to know how the tool worked, and they were very open with that, and that was very nice. And that's why now Petrobras is able to not only Petrobras, but anybody that is interested in using that simulator can use it, and hopefully get more out of the software and of their own data. And in the process of implementing this tool, we realized that the simulator, the UT simulator, had an artificial cap at 200 ohm meters, so we removed that, and now the logs are going to be matching a little better, even for high resistivity. Something else that we've done because of sponsors' feedback, Michael Rabinovich wanted to be able to simulate 2D resistivity logs with an ideal borehole or with a true, he basically wanted to simulate raw logs. And that the way we had it set up was not possible. So we modified it so that you have these three options. You can either have the ideal borehole, which is how the logs are going to be provided to you by the service company in most cases. But then you can also have the no correction, closer to what you would get from the raw logs, and something called variant tool logs, which is just using the corrections implemented by the external program. That is going to depend a little more on whatever the external program implemented. Then also something very simple, but very useful, is if you're in a situation like this where you have your tracks, and then you have open space, but you want to use it, now we have this tiny button here that if you click it, it makes it fit. This is something that people had asked for, I think, for a while. We just hadn't come to do it. Now it's there. Hopefully, it makes your user experience better. The fluids are now a single entity. This is something that we've had in the past, but just from the palette point of view. This is the fluids zone for the palette. And we had the density of the fluid, regardless of the water saturation, regardless of the fluids you had. This was the fluid, not saturation, density, and sonic properties. And they were the combination, and that was great. But some people wanted to see this not just for that one fluid, but for the entire interval. So for different layers, how would that look like? So what we had to do is just turn that into properties, Earth model properties, so we keep adding Earth model properties. That's one big thing that regarding user friendliness. We need to not reduce the number of Earth model properties, but just make the useful ones more visible. We'll do that this year. And now it's easier to do it, and they depend on each other through density. It makes it easier to also, if you're going to work with the bulk modulus or with the slowness, it's going to be consistent regardless. And on that line, we also simplify the database, and if you modify one, you're modifying the other. Something else is somebody was working with image plots, and sometimes this data, NMR or sonic data, sometimes they were just loading them as image rather than the raw data, just because of the processing and the space and all that. But they wanted to modify the limits. So it was easy. We just added some option here. And if you, for example, change this to 0.8, you can see that it's going to change that. And you can zoom in the areas that you're more interested in. Something very silly, but actually useful. When you do the MCMC inversion, the improvements are local. And at the end of the inversion, now we add an extra step that just combines all the local improvements. And sometimes, in this case, the misfit goes a little bit higher. But it's important because this is the true last misfit that you would have. So when you start doing things a little more quantitatively, it's important to have exactly that. And if you restart the inversion from here, you should always, it should be exactly the same RMSD than the last one. And that was not happening, now it's happening. Also, somebody wanted to just save a couple of wells instead of the entire project to save space and to make it easier. So now you can just click here and say, I only want to save certain wells. This is going to pop up. You just check on the wells that you want to save, and you're done. You can open that as an independent project, or you can also append those wells to other projects. So if you want to work independently in multiple wells and then you want to have a giant project with all of them, you can do that now. Somebody wanted to be able to reorder the mnemonics. This is something similar to what I was talking about with the Earth model properties. There are some that are more used than others. But to make it easier, that person wanted to have the mnemonics that they use the most higher up in the ranking or have a higher order. So they display here with the order that they have. So it makes it a lot easier when you're making the selections for those people that have been using UTAPWeLS. You know that this list can go on and on and on. You don't want to see that. You just want to be able to work with the few curves and the few properties that you're going to be using in the specific project, make it a lot easier. So we have that. Also, this one is actually pretty interesting. Julio was working with lithium chloride and wanted to model that. So he came up with a couple of plots that were needed to be able to model it, and now we have it here. So when you're adding salinity, you can, in general, you just add it as sodium chloride equivalent. Now you can include lithium chloride. And that's going to affect the fluid density and water resistivity. I think there's another couple of salts that he's interested in including. We're going to include them. In the past, some sponsors asked for these other salts. So if you have another salt in mind, we can include it. And now, looking into the future, we want to be able to identify rock classes a little more programmatically. That's one of the things. In the compositional joint inversion, we want to speed it up. It works great, but the cost for making it a lot better was speed. So we want to reduce the speed as well. And we want to be able to use logs as inputs. Right now, you can only use Earth model properties. For resistivity, if it's been corrected, you for sure want to use the Earth model property, but there's some logs that you don't really need to model depending on the conditions. For example, density, the inversion is not going to change much the value. So you probably don't want to spend the time doing that. So we want to allow you to not spend the time doing that. We also want to have a module to refine the rock physics models. We're making progress on this. We have some scripts, we just haven't put them here yet. And this is to estimate Archie's equation parameters, for example, or physical properties like density and gamma ray from the cross plots and using deciding which model you're going to use, and even design the shale that you want to have, even the formula, depending on, you can select which are the points that have that you believe are 100% shale, And using those points, we can minimize the properties that you believe are true to that shale, including gamma ray, including other nuclear properties, including density, and make it better. We want to integrate the developments that we've done for UDAR, for non-crossing boundaries, that's already working in a course model. We want to include that back and make it available for all properties. That's a development that exists, we just need to connect it. We want to have a module for more efficient transfer of properties across layers and across multiple wells. Drag and drop sounds great. There's extra things that you need to know. What are you actually dropping? What are you actually dragging? And those things. But we want to make sure that that's possible. We want to expand some of the QC plots, for example, candle plots. I think it's time to re-engineer and refactor the fluid flow information testing module. It works really fast. It went through an iteration of refactoring about 3 years ago, and it turned out to be 2 years ago, something like that, and turned out to be a lot faster. Now it's time to make the user interface easier to work with, and also faster to save, and some of the visualization needs to be improved. So I think that's one of the things we want to spend some time this year. Similarly, the Sonic Studio needs some re-engineering and expanding. There's some scripts that we have that need to be implemented. We're working on that. We want to separate shale by structure. That was one of Alice Ekvali's key points in his dissertation, and we've been talking about how to include this in the software with Carlos, and we have some good ideas. We should be able to include that. We want to be able to expand the radius of inversion module. We want to include different invasion fronts. Right now we only have piston-like. We want to be able to include porosity and permeability models as the input, so that the results end up being as closely as physically realistic as possible to what we're observing in the field. We want to expand Python capabilities. We've talked about that. User interface. And as always, feedback is always welcome. So we're here to hear what you want to say about this. To find UTAPWeLS, you know, the webpage is just Google it, or just email Ray or myself to get any of those. The YouTube channel, we've had that for a while, but we've been trying to keep it up to date and trying to show anything we've done recently there. We have the GitHub repository. We have a few scripts. If you're interested in scripting, they're a very good place for starting any script that you may have. This is my email. I usually answer faster on my personal email. This is the email that we have as a team. The benefit of this one is that if I'm out, Bruce is going to be able to answer that one. We had 137 licenses, 20 more than last year, which is good. I hope that the trend continues and grows even faster. The emails and videos, we've done enough. And we started sending regular bi-monthly updates with release notes. It started as monthly, but really bi-monthly seems to be the sweet spot regarding significant developments. We don't want to spam you too much, and we don't want to just say, hey, now you can change the color. Now we want to send something that is actually relevant. Regarding outreach and talks, we had a meeting with Baker Hughes with an introductory webinar and a follow-up visit by them. We got really good feedback, especially regarding fluid flow. That's one of the reasons why we think it's time to significantly refactor that. We had a software overview webinar over the SPWLA's France chapter. Hopefully we get more users from that. We had a workshop last year after the meeting, and that workshop was a little different from previous workshops. Things have been changing, and for the first few years we were doing a very similar starting crash course after the consortium for new users, and we had new exercises every now and then, but it really aimed at people that had never used the software. At some point we realized that the people that are coming to the workshops are people that already have some certain experience of the software. So it's not a good idea to go over, okay, here's how you open things. It's not a good idea to go over the basics. They already know that. So last year, the people that stayed were in that category. So we started just talking about the software openly and going over some of the things on their project, some of the things that they are particularly interested in doing. And we got some and I think it went well. So this year, what we've done is we put an online crash course. You've probably seen it already. You got an email about that. It's very similar to the crash course that we used to have, updated, of course, because the software has been changing. And the idea is that anybody can start using UTAPWeLS whenever they decide it's a good time in their projects. We've had a couple of people, a number of people every year, that they start on their own. We try to make the software as intuitive as possible, so that if you are just starting from the software, we want you to be able to do that. But having those 4 or 5 videos that show you how things can be done can be really useful. Along with those videos, there are some exercises that there are sample data, and you should be able to get on board and start using it. Not just you, but new people in your team, instead of having to wait and have another crash course and so on. Just go online, do that, and if there's specific questions, and this happened many times during the year, we can do one-on-one Teams or Zoom, and we always have time for that, and I hope you guys take advantage of that. And if you need some more advanced, if you have a project that you think would benefit from a visit, we can always do that, and not just go over the more complicated modules and some of the things that are not so streamlined. And for this year, we have the same thing. After the consortium, we have the 3 days of workshop, but really it's very, very open. On Wednesday, we're going to go over an exercise with the compositional joint inversion, just because that's probably the biggest, development for this year. So we want to make sure everybody can use it, and we have some toy data that we can use so that you get some hands-on experience. And then Thursday and Friday, it's open. We already have people that have projects in mind, which is great. Cesar has some ideas about what to do. And if anybody else wants to join us, you're always welcome. And with that, I just want to thank you, and I'm open for any questions you may have. Ali.
I have 3 questions.
Yeah.
Are we guys one by one, or?
One by one.
Let me bring the microphone.
I have the other one.
You can take the other one.
Thanks, Joaquin. So this UI figure, the faster rendering of the figures, what MATLAB version do you need for that?
So they started with the UI figure, like I said, like 8 years ago, but it was not all there. They really started getting better around 21, 22. The one we are using is 23B, so it's better to have 23B. But at some point, they were making too many changes, and it was so bad they were making so many changes that programs that had been developed a year ago were not working anymore, and that was a real problem. That was around 2016, 2017. And in the software ether, people are saying, okay, we need to stop that, and people have stopped doing that. So now it's a lot more consistent. Before, people would ask me, hey, which software version should I use? And I would have to tell them exactly this one, because one before and one after would just not work. That's not the case anymore. So if you have something 22 or even 21 or more recent, you should be okay.
Okay. The other question is about this Python and
Interface.
UTAPWeLS. So, is it like you're calling Python from MATLAB, through the wrappers that they have, or?
So we have things that do that. For example, the Delicio that we use in UTAPWeLS is doing that. But no, what we want to be able to do is to have it fully Python. So from Python, you can open a UTAPWeLS project. So you can work in UTAPWeLS, save your project, and then open it from Python and import it to whichever software you're using. That's the idea. And then depending on your feedback, we can expand the capabilities so that from Python, not only you could open the project, but do some simple tasks. We have some sponsor that wanted to be able to just detect boundaries. So that is working. But we may want to expand that and even run simulations, but that depends more in your feedback. But I think it's probably worth it. Now, AI is not going to solve all the problems, but coding time has actually been reduced by using these type of things. Is exactly the type of things that AI can help. I've used it a couple of times. It's not perfect, and you have to be extra careful because the mistakes that it makes are very dangerous because it works. So you give it a scripting in MATLAB, and then you say turn it into Python, it will do it, and it will work. But in many cases, it's not doing what the MATLAB script was doing. So you have to be a lot more careful than most people think. But it's still, even if it's making a mistake, if I design a test saying, okay, these are the inputs, these are the outputs, it's very easy for me to point where, or it's easier for me to point out where the problem is and correct it. It's a lot faster than starting from scratch. So the transition would be a lot smoother if there's enough interest.
So, okay, so there's an ask is like, okay, if I want to, let's say, run a simulation in UTAPWeLS and bring it to my either MATLAB or Python environment, like how are you envisioning this, like going back and forth between?
So right now, you would have your UTAPWeLS project, and then run the simulation right now. Run the simulation, save it, and then you would load it in Python in whatever environment you want. Now, what we can do is, and we can work specifically in the things, like for example, if you tell me, I want a resistivity simulation, can we do it in Python? I can turn what we have in MATLAB already into a Python script. It's not done, but we could do that. And so that way, if you're in Python, and as you know, you could be in Python from inside IP or inside TechLog or inside Geolog. I have to name all three of them. And if there's more, I apologize. And inside any of them, you could just say, call UTAPWeLS inside your script. And with the data that you have, just run whatever you want. Simulate this, detect boundaries, populate properties, do all the things that you want to do with that data, with the MATLAB, with the UTAPWeLS operation. We could turn them into Python. You could run them inside your software and then propagate it. And that's the power of it. You wouldn't have to go to UTAPWeLS. UTAPWeLS would go to your software. That sounds very like a commercial, but yeah, that would be the way to do it. I think that's the future.
Okay, so you still need to like basically have that saving aspects and moving it to the...
Yes, right now we still need to have the saving.
Okay.
Yes.
And last question. So in the shared composition manager that you had, so you said for Neutron you are using UTNeutral, right?
We're using UTNeutral.
So it's like calibrated to the Longhorn tools, Longhorn Neutron tools then?
UTNeutral, I think it's tool independent.
Yeah, UTNeutral is a property.
It's just like...
No, but there you have the N-phi calculation. N-phi is...
The neutron process.
the neutron porosity.
Yeah.
Yes, the calculations really are in migration length. That is true. And then we just use, yes, you're right. The equivalent is in the Longhorn. Okay. But we could do something different if you have an interest. Yeah.
Right, thank you.
If not, we're on time for your demo.
Yeah, and I can probably start the demo, and if there, Nadia, or ask the question, and then... Oh, okay. Okay. Yeah, I can probably start the demo.
Okay, so the next thing is, since Linda, we're on time, Joaquin is going to show a very quick demo on the compositional how it is developed. And then we have a break at 10:45.
So this is just a quick demo, and I wanted to go over... Is this one on? No. I wanted to I can turn on so that I can use... Okay, I'm going to use this one just so I can have both hands here. Okay, so here I just have a project, and one of the things I wanted to show you a few things really rapidly. So if I have some LAS files here, and if I select them, these are two LAS files that I got from a public repository, and I can just drop them. I don't know if you saw that, I just dragged and dropped. That was, and it's it's just going to ask me if I want to make a new well for each file. I say okay, and it's telling me, okay, do you want to import all the logs? I say yes. And now for the other well, and now we have the two wells. So that makes it a lot easier, a lot faster to import data. That was one of the things I wanted to show you. Then also in the crossplots, there's no magic here. There's nothing super new, but it's very fast, and that's exactly what I wanted to show you. Here, I just need to select which well I want to see, and it's going to update really fast, or much faster than it was. And I can have multiple plots here, and they have different overlays. This one doesn't have all the data, so it's not going to show it. But this one does have the data, so it's actually showing it. And I can go back to density neutron because we have multiple overlays. So for example, here we have assuming fluid density for 1.19 or 1.9, and you can see how the curves change. You can hide it if you prefer. You can show it. These are the same things that you would have. You can change the limits to make sure they all show, change the limits to default limits. You can show multiple wells if you want to. You can select all the wells you want to show, and it's showing that quickly. You can decide which markers you want to use, or if you want to separate the markers by what. So I can just show them here. I can hide them. These are simple things, but they can be very useful. And again, it's just trying to make it as easy as possible. That color is not good, but that's okay. Anyway, so this was just one of the examples I wanted to show you. I also wanted to show you really rapidly. Yeah, we have time. Really rapidly how the dev shift works. So we have this one here, this icon, dev shift, or within the logs. And it's just going to open something that looks very similar to the track display and has the cow correlation optimized warping algorithm. That the reason why we chose it is because there was this review paper, very thorough, very nice, by the way, 2023, relatively recent, where they made a test of all the different algorithms they had, including AI, and the one that worked the best, and maybe AI has gone a long way in the past couple of years. We know it has gone a long way in the past couple of years. But the one that worked better was just correlation optimized warping. So basically, see what is the correlation between different logs and see and line them up. So what we have is we just have a reference log here, and then we can add whichever logs you want to align. So I can say density, for example. And I just these are the parameters. I'm not going to go too deep into the aspects, but you can just click apply, and you will see these lines that are the anchors. And then I can zoom in and see how they look like. Not only how they look like, well, so you have the original is in solid, and then you have the one that was shifted in dashed. And you can see in this case, for example, it's trying to make this correlation a little better. You can see that those two and those two. And if you think that's not correct, you can just move it whatever you want. You can change the parameters for this, and then you can just save it. And it's going to save it in a different log set that's going to have the depths that you want. Should be easy to use. This was something, nothing too new, but useful, and it's very straightforward. I hope it's it's very intuitive to use, and I hope you guys get to use it. And then the last one that I wanted to show you is I have this well prepared for the joint inversion. Sorry. Where I've already inverted for the physical properties, meaning gamma ray, density, resistivity, and so on. These are going to be physical properties. Also, I wanted to show you how easy it is to switch between one template and the other. And then now it's just showing those properties. And I'm just going to make it fit. And but now we want to do the joint inversion. So we just click in this button, or inversion, compositional joint inversion. This is what I described. You have the inputs, you have the outputs. You can change the shale structure. And then you go into any of these components. And you can, I'm just going to use shale instead of more minerals, but you could have any other mineral you want. This is just the shale that I designed to make it a little easier. You can have different porosity, you can have it flexible, and anything you modify here is going to be shown here. And you can, I'm going to consider invasion because I know this is a piston-like invaded case. And it's going to calculate permeability, hydrocarbon pore thickness. And when it's done, it's going to open the diagnostic plots, which is something we had in the past. You may remember. It's just a comparison of what we're doing here is we have the inputs, bulk density, photoelectric, and so on. And then we have the properties that we're going to invert for. So it's going to be all the volumes, the porosity, the water saturation, and the mineral volumes, including the shale concentration for sure. And then, assuming that the results that we're getting from that inversion are correct, is going to generate a property that corresponds to it. And these are the diagnostic plots that we have. In blue, you have the property that we gave as input, and in dashed red that you can barely see. Let me make this fit. And let me just change the limits here so that we can actually see it, 2000. And by the way, if you click in this one, it makes all the limits in that plot match. You can barely see the dashed line because it's on top, which is exactly what you want to see. This case is, and not only this curve, but all of them are exactly on top of each other, which means we got the complete optimal result. This was a match. This was not over-determined or under-determined, so it's just a perfect match. It's one of the simpler cases, but that's exactly what we want to see. If you remember in previous iterations, there was always a bit of a mismatch between these two. And if you actually pay attention, there's a little bit of a mismatch. But so for example, here for photoelectric, while the target property was 3.223, the property we got was 3.217. So there's a very, very small mismatch, but it doesn't matter. For this case, it doesn't really matter. And now, so it's just telling you if things are right. One of the advantages of this algorithm is that it can handle underdetermined or overdetermined cases. The only thing that's going to change is just the confidence intervals. And if you see, if we go back to the track display here, instead of physical properties, now I'm going to go and see petrophysical properties, which are the outputs. Now we're going to see how that changed. Let me actually, I don't like this line, so let me actually open it again. And we're going to see the confidence intervals that we have. And so now we have the porosity, and we have confidence interval for porosity, we have water saturation, hydrocarbon pore thickness. We should, let me make the limits a little better so we see the whole thing. We have the hydrocarbon pore thickness, and we have permeability in the last one. And you can also see how that changes. We can also see independent components. So for example, quartz, we can see, and not only that, but we have confidence interval for it. And because we're inverting for both zones, the invaded zone and the virgin zone, and I'm going to have a talk, and you're going to remember this for this after this meeting. You can see in this case that the invaded zone had, the fluid was mostly water, or water-based mud, and then the virgin zone had mostly methane. And you can see those changes here in just the volumetric plots. And that's just a little demo that we had. I only did it in 4 layers because it is slower than the previous one. It takes about 10 seconds per layer, or per point, per data point, which of course is more than what we want it to be. But considering the improved results that we're getting, it's worth it. And we're still hoping to speed it up. We know you're in most of real projects, you're going to be working with not 4 nor 10, but hundreds of layers. So we want you to be able to do it at least after coffee, not a whole overnight. So that's the goal. And I don't know if there's questions on the demo or comments. Cesar. Which one? Yes. So the hydrocarbon pore thickness is going to be very close to that. We can modify the calculations and we can add properties. That's something else that we can do now. So it might have to be an after calculation, or we could modify it to do it. But right now, the hydrocarbon pore thickness is as close as it gets. It's just whatever the volume for hydrocarbon is times the thickness.
TOC.
So right. No. So I think we would have to modify it to see it. But so you want to include it as a component?
Right, as an output, like the same as porosity, water saturation, V clay, and then TOC.
TOC. That would be similar to quartz. So it would be another mineral, or?
No, you have to enter the composition
Yeah, okay.
Right.
Yeah, yeah, exactly. You would just have to give it as another fluid, and it would be similar to water saturation, or similar to quartz. Sorry, similar to quartz. You could here.
So we used to have that, I think, but somehow that, and also in that case, you don't have invasion, correct? So
Right. Yes. But it would be treated. Yeah, we just need to define it there. In the outputs, it would not. For fluid, we have. So it depends how you want to do it. If you want to do it fluid, we can just put it here. But we have in solids, so you could say it's part of the matrix. You could just add another one similar to what we did with quartz, and you could just have kerogen or any of those, and it would give you the result. And these ones, you can see what the properties are, and if the properties that you have for the kerogen that you're using are different, you can just change them here. But that's already working. That we don't need to change anything. That's possible.
any other questions here?
Uh-huh.
Microphone coming.
Great presentation. The auto depth shifting is a pretty cool feature. Now, for some operators, we use TechLog, for example, for our workflows. Can you run us through, how would the Python functionality work? Let's say if I just want to run the auto depth shifting and see the results in TechLog,
So-
can I call up the library of the
Talk to me and I'll do
database?
it. I just need to translate the MATLAB part to TechLog. It's not difficult. It'll take me a couple days. But yeah, that's exactly the kind of thing, the kind of feedback that can be very useful. And the advantage is I can do it for you. And once that's done, it's available for everybody. So we can do that. Yeah.
That'd be great. Thank you.
Good. Khalid?
Thank you. Thanks. I have just a question about the simulation. Are you still updating the resistivity models with the resistivity tools from service companies? And did you add any new ones?
The only one we added this year was that EWRP4D, or I'm not getting it right, but that's the only one we added. But we still have the general induction tools in 1D and I believe 2D also. So if there's a specific tool that you think we should add, it's a matter of doing the same thing that Lucas from Petrobras did. Just contact us and contact the service company, and they're usually very happy to work with us. And we just need to get the settings for that tool, and we can add it.
Okay, thanks. And I have seen that you do have RVRH. So can you model or simulate for vertical resistivity and horizontal from other tools like ZIT or from 3DEX?
Yes. So we have some tools can take into, or some simulations can take into account anisotropy. If that simulator can take into account anisotropy, we can invert for those two. And we have some constraints to make sure one is larger than the other, and so on. But we need to make sure that the simulator can do it. The good thing about that one is that the 1DUT semi-analytic can do it. So chances are we can do it. And,
That one we don't have. The SOP.
so artist scanner, yeah, we don't have that. So we need to insist with that. Ali.
So I noticed that you're using multi-physics depth shifting in that way. So you have the density and you have the gamma ray within
Right.
As far as if you want to do the gamma rays,
Yes.
gamma rays match.
Yeah.
So first of all, I don't know if you have an example of that to show, but like my question was, a couple of years ago, they had this AI competition for the depth shifting. Did you get a chance to look at what they did and the winner, what method they applied?
No.
Yeah, I think that would be something very interesting.
That'd be cool, yes.
For the multi-physics one, but
Right.
for the standard one, I think this works. I don't know if you have any demo like to show
But-
for gamma rays or.
No, but something that I can do, I probably went a little too fast on that one. Something we can do with that one is, even though, this is not the one I was it? Even though I did it for just one, if instead of density, you would have, if you had something from, I only have one log set, but if you had another log set, you could do that here. And if you wanted to do it, right now is the correlation just between gamma ray and density porosity, but if you had it multi-physics, let's say not, you could have another gamma ray, but let's not use the same gamma ray because it's going to be pointless. But let's say neutron, you have those two, and you run the cow, it will do it with both of them. And right now it seems like it did it, it didn't change anything, which means that the correlation of both was the same as the one, at least in this area. But it would take into account the correlation of both. So it's not, would this count as multi-physics as you were describing, or?
Yeah, I think that's the idea. Like you want to
Yeah.
make sure that all the
Yes.
logs that you use for the
Yeah.
interpretation are on depth. And this becomes very important, like the very deep wells, where the cable movement is quite severe and you have very laminated reservoirs. That's a problem. So if this problem can be solved, I think it makes
It would be great.
many people happy.
Yes, from the user interface point of view, of course it gets too busy to have all of them, but from the practical point of view, that's very much possible.